Okay, we're going to be looking at the next section here, specific heat capacity, heating and cooling. We just looked at some of the basics of energy. So the goal here is to use specific heat capacity in calculations of energy transfer. Transfers as heat involving temperature changes. Okay, so first about specific heat capacity. This is the energy required to raise 1 gram of substance by 1 degree Celsius. For example, the specific heat capacity of water is 1 calorie, and that's defined. So it takes 1 calorie of energy to raise 1 gram of water by 1 degree Celsius. Now, since 1 calorie is 4.184 joules, we could also say it's 4.184 joules per gram per degree Celsius. Now, it turns out that the temperature is really a change in temperature. So 1 degree Celsius change is the same as a 1 K change. So degrees Celsius and K are interchangeable. So we could also say 1 calorie per gram per Kelvin, or 4.184 joules per gram per Kelvin. This is a number you want to memorize. 1 calorie per gram per degree Celsius. Again, this has infinite zig figs because it is defined. So we just talked about this for specific heat capacity. It's 1 calorie per gram per degree Celsius. This part up here, this calorie, is heat, which is given the symbol Q. This is the mass, which is given the symbol 1, or M. And this is a change in temp, which is given the symbol delta T, which is T final minus T initial. Sometimes your change in temp can be negative. Sometimes it can be positive. If you start at 0 and go to 100, that's positive 100. If you start at 100 and go to 0, that's negative 100. Okay, so this is the formula you want to remember for specific heat capacity. Q or C equals Q over M delta T, or Q equals CM delta T, one or the other. They're both the same. Sometimes you're solving for C, sometimes you're solving for Q. Sometimes you're solving for T. So let's take a look at some problems here so that we can see how to solve them. So the first one here we have is that the molar heat capacity, let me get some paper here. So here we have the molar heat capacity of mercury is 28.1 joules per mole K. What is the specific heat capacity in joules per gram K? So what we're going to do here is we're going to take this 28.1 joules per mole K, and we want to take this mole and change it into grams. So naturally, we'll want to multiply by mole here and gram here. So what type of conversion is this between grams and moles? It's molar mass. So we're going to look up the molar mass of mercury. So I see the molar mass of mercury is 20.59, 200.59, my apologies, per 1 mole. So what'll happen here is the moles will cancel. The K doesn't cancel, the gram doesn't cancel, and neither does the joule. So they remain, and they remain where they were before. That is in the numerator or denominator, whichever place they were in before. People normally put the gram before the temp, so we do that. And here, 28 divided by 200 is going to be a pretty small number. So 28.1, 3 zig figs. Divided by 200.59. And we get 0.140 joules per gram K. So that is the specific heat capacity in joules per gram K. Let's take a look at another problem. The specific heat capacity of copper metal is 0.385 joules per gram K. How much energy is required to heat 168 grams of copper from negative 12.2 degrees Celsius to plus 25.6 degrees Celsius. So what I'm going to do here is I'm going to flip this page over and we're going to start anew. So we got the specific heat capacity of copper is 0.385 joules per gram K, which is equal to 0.385 joules per gram per degree Celsius. Degree Celsius and Kelvin are interchangeable because these are changes in temp. We have here that the mass of the copper is 168 grams. And lastly, we have the change in temp of the copper is going to be 25.6 degrees Celsius minus negative 12.2 degrees Celsius. So here we have to be careful. Remember, for a change in temp, it's final minus initial. If the initial is negative, then it's going to be minus a minus. Okay? So if we add this all up, the change in temp is going to be what? 37.8 degrees Celsius. So we have our three values here. And now all we have to do to calculate the energy required is to use the formula Q equals Cm delta T. So C is 0.385 joules per gram per degree Celsius. So I'm going to put parentheses around that. The mass is 168 grams. So I'm going to put parentheses around that. And the change in temp is going to be 37.8 degrees Celsius. You can see that the degrees Celsius cancel, the grams cancel, and we're left with joules. And let's see what we get. Looks like it's going to be a pretty big number because this is about a fourth of that. So, excuse me, 40% of that. So 40% of that has got to be around 70. And then 70 times 40 makes it like 2,800 or something like that. So 37.8 times 168 times 0.385, and we get 2,440 joules. Three significant figures, three significant figures. And there's your answer. Okay. So what would I expect to see on the test? I'd expect to see this. I'd like to see that. I expect to see that. And you don't need to make a list, but it is nice to make a list. Okay, let's try one more here. The initial temp of a 344 gram sample of iron is 18.2 degrees Celsius. If the sample absorbs 2.25 kilojoules of energy as heat, what is the final temp? So the Q is 2.25 kilojoules. The mass is 344 grams. The initial temp is 18.2 degrees Celsius. And the specific heat capacity we have to look up. It's in our book, usually towards the beginning of the chapter in a case like this. And so here, I'm going to be looking at iron is 0.449 joules per gram degree Celsius. Okay, so in this case, let's try and figure out the formula we want to use. So I have Q is equal to Cm delta T, which is Cm T final minus T initial. So Q divided by Cm is T final minus T initial, which means that Q over Cm minus T final is equal to negative T initial, which means, I'm going to carry this up here, that T initial is equal to See, I'm taking the negative of T initial, which means I need to take the negative of T final. So that's a positive T final minus Q over CM. So that's my formula for getting the initial temp. So when I plug the numbers in, T final is 18.2 degrees Celsius. And here, remember, for this particular problem, the initial temp is 18. If the sample absorbs, so if this absorbs energy, what is its final temp? We expect the final temp to be higher. Oh, I solved this for the initial temp. So I've got to cross this off. And I've got to do this. T final is Q over CM plus T initial. I didn't read the problem carefully. So what is the final temp? So Q is 2.25 kilojoules. C is, what do we have? 0.449 joules per gram degree Celsius. And M is 344 grams. So this joule cancels with that joule. This gram cancels with this gram. And the T final, and I need to put plus 18.2 degrees Celsius. Okay, so now I just have to put all these numbers together. Remember, this K, I can substitute 10 to the third for because K means 10 to the third. So I've got 2.25 second EE 3 divided by 0.449 divided by 344. And that comes out to be 14.3 zig figs here, 14.6 degrees Celsius plus 18.2 degrees Celsius. Add those two together, and we get 32.8 degrees Celsius. And there's your final answer. All right, so moving on. We have a lot of problems to cover here. I want to go over a lot of examples for you to look at. So here's another example. How much energy must be transferred to raise the temperature of a cup of coffee, 250 milliliters, from 20.5 degrees Celsius, 293.7 K, to 96.5 degrees Celsius, 368.8 K. Assume that water and coffee have the same density and specific heat capacity. Okay, so here we know that the specific heat capacity is 1 calorie per gram degrees Celsius. So we can do this in degrees Celsius instead of Kelvin. You'll notice in this case, if we look at the change in temp, it's going to be final 95.6 degrees Celsius minus initial 20.5 degrees Celsius. And here, if we take a look at the difference here, we get 0.1, 5, and 75.1 degrees Celsius. If we do the change in temp in Kelvin, we get 368.8 Kelvin minus 293.7 Kelvin. And the difference here is going to be 0.1. And then we have 8 minus 3 is 5. And then we have 36 minus 29 is 7. So you'll see that the change in temp has the same numerical value, just different units. So for all practical purposes, the degrees Celsius and the Kelvin are interchangeable in these problems. Okay, so we've got the specific heat capacity of water. 1 calorie per, oh, and we're not going to use this value because they give us this value. So the specific heat capacity is going to be 4.184 joules per gram K. And so I'm going to use this K because they gave us that value in K. Now, what do? We have 250 milliliters of water, but we need the mass. So to get the mass, we're going to start off with 250 milliliters and multiply by 1.00 grams per milliliter, which gives you 250 grams. Okay, so we've got the mass, we've got the change in temp, we've got the specific heat capacity. All we have to do is solve. So Q is equal to C M delta T, and we have 4.184. Let me move this up just a little bit. Joules per gram per Kelvin. The mass is 250 grams. And the change in temp is 75.1 K. So when we do all this work, we can see it's going to be a pretty big number, but we can still estimate because 250 times 4 is 1,000. 1,000 times 75 is 75,000. So the answer should be around 75,000, maybe a little more because that's not 4, it's 4.184. Okay, so 4.184 times 250 times 75.1 is equal to 79000. And the K's cancel, the grams cancel. We're left with joules. Now, why only two significant figures? It's because of the 250 here. So there's that problem. Alrighty then, here's another one. A 13.8 gram piece of zinc is heated to 98.8 degrees Celsius in boiling water and then dropped into a beaker containing 45 grams of water at 25 degrees Celsius. When the water and metal come to thermal equilibrium, the temperature is 27.1 degrees Celsius. What is the specific heat capacity of zinc? So what we have here is a piece of zinc, and it's 98.8 degrees Celsius. And you can achieve this temperature by putting it into boiling water, and the zinc will heat up until it's the same temperature as the boiling water, which is usually closer to 100 degrees Celsius, but it can be less than 100 degrees Celsius depending on the conditions. So you got this hot piece of zinc, and you got this container of water, and the water you've got 45.0 grams, and it's at 25.0 degrees Celsius. Now, when you drop the zinc into the water, of course, the level on the water rises. Here's your zinc. And the temperature final is 27.1 degrees Celsius. All right. So is this the final temperature of the zinc, or is it the final temperature of the water when it says that the temperature is 27.1? And the answer is it's the temperature of the zinc and of the water because of thermal equilibrium. So remember our definition of thermal equilibrium. It's when objects that are in thermal contact reach the same temp. All right, so we're going to split this into two problems. The first problem is going to be, and so I'm going to split this into two. We're going to calculate heat absorbed by the water. So we're going to use the formula Q is equal to C M delta T, which is, let's see, we're going to go ahead and use, calories because it's exact. 1 calorie per gram degree Celsius The mass is 45.0 grams. And the change in temp is going to be, for the water, 27.1 degrees Celsius minus 25.0 degrees Celsius. So here we'll have a 2.1 difference times 45 puts us at about 100, times 1 puts us at about 100. So let's see what we get for our answer here. 45 times 2.1 is equal to 94.5 degrees Celsius. Now remember, the difference here is 2.1 degrees Celsius. It's only good to the 10th because both of these are good to the 10th. If this is good to the 10th, this has 2 zig figs. And so here, this should really be 95 degrees Celsius. Okay, so that's the amount of heat absorbed by the water. Oh, and it's not Celsius. I didn't cross my units out correctly. It's calories. So it absorbs 95 calories of heat. Now, the zinc releases heat. That makes it exothermic. And the amount of heat released by the zinc has to be the same as the amount of heat absorbed by the water. So here, the Q for the zinc is negative 95 calories. Remember, exothermic means negative. So you might be wondering, can you really have a negative value for heat? And the answer is absolutely. It's just the direction of heat flow. So this says heat is flowing from the zinc. There is no positive or negative heat or energy. It's just the direction of which way it's going. So here we want to solve for the specific heat capacity, which is this. And remember, we want to use the values for zinc here. So in this case, the Q of the zinc is minus 95 calories. The mass of the zinc is 13.8 grams. And the change in temp is the final minus the initial. This is the final temp of the zinc, 27.1 degrees Celsius. The initial was 98.8 degrees Celsius. And you can see that this difference is going to be a negative value. And then when you have a negative value divided by a negative value, it becomes positive. So our specific heat capacity for zinc will end up being positive. So let's see what we get. 95 divided by 13.8 divided by parentheses 27.1 minus 98.8 end parentheses. Oh, I made an error somewhere. 27.1 minus 98.8. And I get 0.096 calories per gram degree Celsius. Now, if I convert this into joules, I'd multiply by 4.184 joules per calorie. And let's see what I get. 0.096 times 4.184, and we get 0.40 joules per gram degree Celsius. So either answer would be correct. And this is pretty close to the specific heat capacity of zinc. Okay, let's put that one to the side. I'm going to pause this for just a minute, and then we'll take up from here in just a moment. Boom. Okay, the next problem I'm going to be doing is this one right here, a 182 gram sample of gold at some temp was added to 22.1 grams of water. The initial water temp was 25 degrees Celsius and the final temp was 27.5 degrees Celsius. If the specific heat capacity of gold is 0.128 grams per or joules per gram K, what was the initial temp of the sample? So first of all, I'm going to draw a little picture. Here's my gold, and it's 182 grams. And here, T initial is what we want. Here's my water. We put the two together, and here's the gold. Now, for the water, what do we have? We have that the initial temp is 25 degrees Celsius, and that we have 22.1 grams, and this is water. Now here, the T final is equal to 27.5 degrees Celsius. And we want to find out the initial temperature of the gold. So I'm going to show you kind of a, well, I'll just do the two-pronged approach to solving this first of all. We're going to solve for how much energy the water absorbed. And that's going to be Q is Cm delta T, which in this case is 1 calorie per gram degree Celsius. And I'm going to make that 4.184 joules because the problem gives us joules for gold. 4.184 joules per gram degree Celsius. The mass of the water was 22.1 grams. And the change in temp of the water is 27.5 minus 25.0. And we can see that when we do the calculation here, we have basically 2.5 times 22, which should be around 50, and 50 times 4.184, which puts us a little over 200. So let's see what we get. 4.184 times 22.1 times 2.5. And I get 230, let's see, grams cancel, degrees Celsius cancel, joules. Now, why only two significant figures? Well, because 27.5 minus 25.0 is 2.5 with two zig figs. Okay, so that's the amount of energy absorbed by the water. So this is a positive value because it's absorbed. And we can see that with the change in temp. So what about the Q of the gold? Well, that's going to be negative 230 joules because this is energy released. So we have to remember that whatever the amount of energy is that is absorbed, the energy released has the opposite sign or a negative sign. So here, we want to find out the final temp of the gold or the initial temp of the gold. So T initial of the gold. I'll go ahead and start off with this formula here. Q is equal to Cm T final minus T initial, which is Q over Cm is equal to T final minus T initial, which becomes T initial is equal to T final minus Q over Cm. Okay, so let's plug the values in here. T final is 27.5. Q is negative 230 joules. And remember, we expect that initial temperature to be higher than the final temp, right? Because the water warmed up. Okay, specific heat capacity of the gold, we are given as 0.128 joules per gram Kelvin. 0.128 joules per gram degree Celsius is what I'm going to write. And then the mass of the gold was 182 grams. So you can see here that when I have the negative of a negative, I'm really going to end up adding in a number to my 270 or to my 27.5. So I'll get an initial temp that's going to be higher than 27.5. So 230 divided by 182 is a little more than 1. Divided by 0.128 gives us around 10. So I think the answer is going to be around 37. So let's see what 230 divided by 0.128 and divided by 182 is. So this ends up being 27.5 degrees Celsius plus 9.9 degrees Celsius. This only has 2 zig figs, so this only gets 2 zig figs. This is good to the 10th. This is good to the 10th. So when we add them together, we get 37.4 degrees Celsius. And there's your final temp. Now, you aren't required to draw something on the exam, but sometimes it helps to do that so that you can keep track of things. Okay, we're just going to do one more problem, and this one is a doozy. I'll just say that. Specific heat capacity. A 45.5 gram sample of copper at 98.8 degrees Celsius is dropped into a beaker containing 152 grams of water at 18 degrees Celsius. What is the final temp when thermal equilibrium is reached? So this is a hot piece of copper. This is cold water. When they combine together, the copper will get colder and the water will get warmer. So here's my copper. I have 45.5 grams and it's 99.8 degrees Celsius. Here's my water. It's at 18.5 degrees Celsius and 152 grams. We combine the two together. Here's the copper. And T final is what we want. Okay, so we're going to need a few things here. We're going to need the specific heat capacity of copper. Now, from a previous problem, I recall it as being 0.385 joules per gram degree Celsius. We'll need the specific heat capacity of water, which is 4.184 joules per gram degree Celsius. We need the initial temp of the water, we need the initial temp of the copper, and we need the mass of the copper, and we need the mass of the water. So we have all of those things right here. Now, I want you to recall that when I get the Q of the water, it's going to be some positive value. But the Q of the copper, it's going to be a negative value. So whatever the water value is, the copper has the opposite value. Now, what happens when I take the Q of the water and add it to the Q of the copper? I get 0. So this basically says that in this particular interaction, if we assume that all of the energy from the copper goes into the water and none of it goes anyplace else, then we can add up the Q changes and they should be 0 because the amount released by the copper should be the amount accepted by the water. So here I've got this equation with both of these. Now what I can do is I can mess with this. So I'm going to put this sheet off to the side. And what I'm going to do here is I'm going to write out that the Q of the copper is equal to negative Q of the water. Or I could write out And this comes from Q of the copper plus Q of the water is equal to 0. Okay. And you know what I'm going to do? I'm actually going to start with this. So here, what's the formula for Q? It's C of the copper, M of the copper, change in T of the copper, plus C of the water, mass of the water, change in T of the water is equal to 0. Now I'm going to write some more stuff out. I'm going to write C of the copper, mass of the copper, T final minus T initial of the copper, plus C of the water, mass of the water, T final minus T initial of the water is equal to 0. Now you'll notice I wrote TF here and TF here. I didn't write T final for the water and T final for the copper because they are the same final temp. Okay, so now what do we want to do? Now things get a little messy. So we get C of the copper, mass of the copper, T final, minus C of the copper, mass of the copper, T initial of the copper. So I distributed these two into this equation. I'm going to do the same over here. C, I'm going to use W for water, mass of the water, T final, minus C MW T initial for the water is equal to 0. Then what I'm going to do is I'm going to put like terms together. The like terms I want to combine are these two with the final. So I'm going to write C of the copper, mass of the copper, T final, plus C of the water, mass of the water, T final is equal to, and I'm just going to go ahead and take these onto the other side of the equation. C of the copper, mass of the copper, T initial of the copper, plus C of the water, mass of the water, T initial of the water. So I did two things in this one step. I put these two closer together and I took these two to the other side. So now I'm going to take my T final and I'm going to divide it out of each of these. So I'll get C of the copper, mass of the copper, plus C of the water, mass of the water is equal to C copper, M copper, T initial copper, plus C W, M W, T initial W. And then you got it. T final is going to be equal to this whole mess here. Divided by this whole mess here. So now it's a plug and chug as long as I have all of these values. So let's see, do I have these values? Well, the specific heat capacity of the copper is 0.385 joules per gram degree Celsius. The initial temperature of the copper was 99.8, I believe. Yep. 99.8 degrees Celsius. The initial, or the mass of the copper was 152 grams. Nope, 45.5 grams. And the specific heat capacity of the water is 4.184 joules per gram degree Celsius. The mass of the water was 152 grams. And the change in temp of the water, or I should say the initial temp of the water, was 18.5. So all of that divided by 0.385 joules per gram degrees Celsius. The mass of the copper was 45.5 grams plus 4.184 joules gram degrees Celsius, and then times 152 grams. Okay, so let's figure this all out. We'll do it piece by piece. So this piece up here is 0.385 times basically 100, and then times 45. So for this value here, I get 1,748 joules. Okay, so here 100 times 45 is 4,500, right? And a fourth of 4,500, does that seem about right? Seems about right to me. Okay, now here I have 4.184 times 152, and then times 18.5. And so for that, I get 11,765 joules. And notice degrees Celsius cancel, the grams cancel for both of these. So that's why I say joules here. Now over here, what do I get? 300 or 0.385 times 45.5. So I get 17.5. And then the grams cancel, so joules per degree Celsius plus 4.184 times 152, 636 joules per degree Celsius. Now I'll add these two numbers up at the top, 1,748 plus 1,1765, and we get 13,513 joules divided by, add these two numbers up, and we get 653.5 joules per degree Celsius. These joules cancel, so I'll get a degree Celsius for my answer. And let's see what we get. 13,513 divided by 653.5. And we get 20.67 or 68 degrees Celsius. Let's figure out what we would actually report for significant figures. Well, this value here gets 3 zig figs, so it's good to the, if you will, to the tens. And here, these values here, you see that we have 3 zig figs here. So this is good to the 1, 2, 3. This is good to the thousands, or hundreds, I should say. This is ones, tens, hundreds. So when we add these two together, they're going to be good to the hundreds. So this is good to the 5 here. So that means it's good for 3 zig figs. These two numbers here, we get 3 zig figs. So this is good to the 10th. Here, this is good to 3 zig figs. This is good to the ones. So this is good to the ones. So we have 3 zig figs here. So we have 3 zig figs here and 3 here. How many are we allowed here? 3 zig figs. So 20.7 degrees Celsius. So that's the final temp. And if we look at our drawing that we made earlier, let me see if I still have it. Didn't I have a drawing of my, oh, here it is. Let's see if this makes sense. So our final temperature is 20.7 degrees Celsius. Does it make sense that when we drop hot copper into water, that the water will heat up a little bit and the copper will cool down? And the answer is yeah. Does it seem like it would heat up that little amount? And, you know, based on the problems we've seen before, yeah, it is a small amount. Okay, well, thank you for listening to this section. Toodles.